Yeah, magic sunrises. That's why we live here. And the cool thing is, Deakin's only 25 minutes away. Quick takeaway to magic. Here's our first surf check option. Tide's out a little bit. Yeah, that wind is really picking up. It's just a bit protected down that way. Better get to work. Next time. Hey guys.
Hello.
Morning, Jun. We try and get ourselves organised for a bit of new X-ray work today. Trying to introduce that sort of single layer spacing.
Yeah, I'm a PhD student here in Deakin, so I think more than a year. We're doing an experiment today. Hopefully this will give me good data. I have a titanium carbide material, which is Maxine. So it's a 2D material, which I use to coat my fiber. So fiber is silicon carbide. So I'm planning on having it make the silicon carbide more tougher.
Cool, okay, let's get started.
We're doing the experiment now. Exciting stuff.
I kind of want to reboot this.
As you can see here, we have different options, different samples. So this one is the single fiber with Maxine. This is single fiber without Maxine. This is a bundle of fibers without Maxine. And then this is a bundle of fiber with Maxine. So we're hoping we can analyze the single fiber. If not, because of the size and the diameter is so small, so maybe we can try the yarn to get the data, but we'll see later. When you go to aerospace, you need to have materials that can withstand extreme temperature, extreme conditions, and ceramics like the one that I'm doing, the coating, is one of the ideal material for that.
The whole idea of why we call it InsitX stands for in situ capabilities. So in situ X-ray characterization, effectively a world first in the sense we have two experiments, but it's using a really unique X-ray source. And what we do is we have an X-ray shutter on one side, and we take the properties of that bright X-ray source and we confine it onto our sample on the right-hand side. And what that enables us to do is looking at scattering structure. And it's a fingerprint of the material itself. At that length scale, well below the size of a human hair, we can look at the performance, so the mechanical properties, the heat tolerance properties, and this will enable us to interrogate that. So on the right-hand side, we're going to look at this sort of interference scattering effect. But on the left-hand side, we're going to do like a radiography experiment. So the idea is, and this is something we haven't done before, Rochelle's going to try and mount her fibre in this loading frame. As the fibre is undergoing extension, we'll use this high-resolution X-ray detector to actually image that. So what we're trying to see is the load that we put in on that fibre, but also if we see any flaws appearing in the fibre itself. So by using X-rays, you can look at the internal structure of that fibre. And that's how you design new materials. So what I would do now before you do, I would go into Exactly. Okay, so that's your first scattering signal from a single...
Yeah, single fiber.
Wow, you are in the lab. You're not at a synchrotron yet. So that's a pretty good start to the day.
Yeah, exciting.
These are the mornings we live for, to be honest. I know it sounds strange. You build this instrument and you don't really think about getting results like this, and then you see them. That's pretty cool. The only real problem in this place is there's no forks.
We need you now again.
Smiley face, yeah.
Let's put some load on this
Okay.
thing. Okay, so can we just get that measurement there, Dave? The Y? 892? Have you got any load yet?
Not yet.
Traditionally, as researchers and research academics and even industry, we access a synchrotron, which is effectively a large-scale, hundreds of $1 million microscope, and that enables you to do many experiments on the fly. What we've been able to build here in-house is an instrument that can do synchrotron-like studies, and that's a facility that Dave and myself have developed just in the later days of COVID. Rochelle asked to do this experiment last week. If you think about that in the context of a synchrotron, you know, you're not going to see any data for, on a good day, 6 months.
We're going to start ramping it up a little bit further though, maybe.
So for example, you have a fibre composite type, and that's a structural component, but what happens if you actually add a battery capability within that component? And that's really what the cutting edge research is now in terms of new materials, and what we're offering is that new capability to characterise those new materials. And you can't do that when you want to do that sort of dynamic in situ testing on a 6-month basis. You really need that continuous turnover, and that's what we're delivering. So if that slope changes, and which is what it's doing,
then it kind of relaxes.
yeah. So it's initially stiff, and then each time you go up, it's a little bit more relaxed, and now it's fully relaxing. Hey?
Yeah.
Keep going, Rochelle.
Let me just save this
She's
one.
a busy one, and we'll just keep commentating on it. We're loading, Dave. We've got loading. We've got relaxation.
Now the pattern,
cool.
the pattern
Yeah.
comes again.
You watch the pattern in the loading.
Yeah.
We've only ever done this work at the synchrotron. Yeah. So yeah, we're doing it in the lab for the first time. So what force are you up to, Rochelle?
Around 29 centimeters.
Wow, cool.
I would have said it's just a Thursday.
Just the usual
Just
Thursday.
the usual Thursday.
Just the usual Thursday. And the really cool thing is Rochelle can't actually leave the experiment because she's doing a dynamic study. Down the other end, we've got the small angle scattering work. So now we've gone to the long camera length. This is actually giving us a measure of the density of the fibre.
Broke.
And this is what this signal is here. So we're hearing in the background that this in situ experiment
Finally.
is just finished.
It
Cool.
works.
Hey, look at that. She's broken. Maxing out the load, it fails. Very cool. High five. Good stuff. Good stuff. Here we go. I'll let you press it. So Rochelle's loading the fibre. Woohoo! Bang! Picking up the load, loading. It fails. That's pretty damn good for an afternoon. Nice work, Rochelle.
Earlier when I'm putting tension and I need to maintain it, okay, I need to focus. And then it breaks.
Yeah, I thought to finish up, you still got one more scattering measurement to do. So this is going to finish in about half an hour.
Yeah.
So I'm going to take this time to go for a quick jog. The older you get, the harder it is to put your shoes on. Technology nowadays.
I wasn't expecting that much of a result, but I got the data I really wanted.
Well, I reckon that's it. Got to keep the coaches happy.
Done. Done for the day.
Congratulations.
Oh, let's go home. Woo. Great day. Not all days go this well, but this one went smoothly.
It's a very productive day.
All the software, hardware, it all behaved itself. Perfect. Let's go home.
Yeah. Thanks, V.
Good job.